Hi everyone, this is Vikas Goyal and I'm going to present you our DIP Capstone Project report on revealing the trace of histogram equalization in digital images. My teammates in this project are Pankaj Vajia and Ravi Shankar from IIT Khargpur. So I'm going to introduce you about this paper. After that, I will tell you the motivation behind this paper and what is the method behind this histogram to complete this project and what is the proposed algorithm which was given in this paper. The main technique used in this paper is histogram equalization. Generally, this popular technique, equalization, is used to improve the image contrast, but nowadays it can also be used to temper the images, and the existing image forensic techniques may fail to detect the HE operation in high compressed and low resolution images. Even an unexperienced person can edit, manipulate, and process images without leaving visual clues with the help of many editing softwares. So the proposed algorithm in this paper to detect whether a given image, either compressed or uncompressed, has undergone the histogram process or not. It is based on the frequency domain analysis of the image histogram, and it exploits the difference in DC and AC coefficients in histogram discrete Fourier transform. It can detect histogram operation even if the image is saved as in JPEG format after the equalization, where most of the existing algorithms fail. We can see that we have the three images. First is original image. Then we applied the histogram equalization operation followed by the JPG compression. Then we also plotted the discrete Fourier transform curves of all the three images. You can see that the zeroth component is a DC component in all three plots. The zeroth component is also equal to the total number of the pixels in the image, which will remain same before and after the histogram equalization or after the JPEG compression. It can be clearly observed that the maximum value in each of the magnitude spectrum plots are corresponding to the DC values at k equal to 0 and DFT of the histogram shall exhibit even symmetry at k equal to n by 2, which is equal to 128 of the histogram equalization DFT plot. We propose to identify the histogram equalization process in image by observing the difference between DC coefficient at x equal to 0 and weighted sum of unique AC coefficients of xk, where k is belonging to 1 to 128 of DFT of a histogram. As evident from the figure, the histogram of an unequalized image is likely to have random envelope, which may abrupt change in its shape, and therefore corresponding our plot in which k belonging to 128 are likely to have larger values, which can be verified in figure. Since it is expected that the histogram equalization process generates an image having almost uniform distributed histogram, therefore the values of the plot where k belong to 1 to 28 are likely to be 0. The similar observation can be made for an image which is JPEG compressed after histogram equalization. This is because when an equalized image of JPEG compressed, resulting in redistribution of pixel intensities in its histogram. However, the overall contour of the histogram will remain almost same and uniform. From the previous discussions using the DFT coefficient of the histogram, we propose the DC normalized difference between DC and weighted sum of AC coefficients of DFT of the image histogram can be used to identify whether the given image is histogram equalized or not, for which this paper has defined the zeta, which is given below in the bottom of the slide, and you can also see the formula of delta, where we will find the zeta for the individual image. We can see that I is the input image and H is the histogram of that input image and X is the DFT of that histogram. We have used a for loop in which we will count the occurrences of the histogram in H1P, and then we will take DFT of H1 and save it to X1. We will compute zeta using the equation of zeta and delta. Then we will compare zeta with zeta threshold, which is and we will get histogram is equalized or not. Now, where is the zeta threshold came from? We have provided very big set of data to this code, and we optimize the zeta through 3 different experiments. We have coded this proposed algorithm in a Matlab, and the link is provided below of GitHub. Thank you everyone for listening me.